the content. So this is the lab agenda. Again, we'll primarily focus on linear algebra. The QxQ review is optional and likely not something we'll get to today, but we will have notebooks available for you to work on if you'd like to have some extra review this week. So the learning objectives today, here's what we really want you to focus on and hopefully get some more practice with. One, understanding the structure of state vectors. So identifying which number represents the contribution of 0 versus 1. So really knowing what you're looking at when you look at a vector. Recognizing what the 0, 1, plus and minus states are in the state vector form specifically. So now that we're looking at state vectors, we will start seeing many other states. In fact, there's technically an infinite number of them, but really these 4 are the key ones for us to understand most of what we're going to talk about. We could really get away with a pretty good description of a lot of things in quantum computing with just these 4 states. It's only in very nuanced, specific contexts that you need more than this, or very specific problems that you're solving. So, and then lastly, we'll look at the normalization, knowing what it means to be normalized versus non-normalized, understanding why we need to do this process, and looking at how to do it ourselves, practicing that. There's also the QxQ review. Again, we're not going to do that. I believe the attendance code is not quite, or the attendance quiz is not posted for us yet, last I checked. So what I would recommend you do is record this down, and I will type it in the chat as well. So 9708. So the attendance code is 9708. Again, I believe the quiz is not posted yet to Canvas. It may have been in the last few minutes, but last I checked, it wasn't. So at the moment, just store this somewhere. And I will get to this in a second. But today is actually really not going to happen in the notebook or on IQX or anything like that. Today is really a pen and paper day. I'll say this is something that physicists really love, is just a day to just do some math, do some pen and paper work to really kind of work out these concepts and understand what's going on. So I'll give everyone a moment. You do not need to open IQX, the IBM Quantum Experience. You do not need to open a notebook, but please do open something that you can write on and get something that you can write with. So if you don't already have a paper and some pen or some way of writing, please go ahead and do that. Please go ahead and get yourself something. I'm excited to see some people excited for math. So yeah, giving everyone a moment to get started. Yeah, this is really where we dive in. This is where we go and kind of peel back the layers and look at the math underneath. It's important as we do this not to lose sight of the physical intuition of what's going on, the physics behind what's happening. That's part of why we believe in holding off on the math, so that you can focus on what's happening, and then the math can help give you a more nuanced view of it. But I believe you're all ready for that now. You've all had a full semester of this, so it's finally time to dive in and look at some math. And if you're not a math person, if you're sitting there going, what the heck, I'm not finally excited for some math, that's okay too. This is a time when we'll also just get comfortable with it. We'll see why we're doing this, how to do it. We'll see it in a few circumstances. This is not a course in vector and matrix math in full. We are just going to see a few key tools that we need to do things that we've already done and do a little more. Okay, so let's get started. So a quick review of lecture, the new topics that we went over. First of all, vectors. This is a word that you will start hearing a lot this semester, vectors. By definition, a qubit state is made of contributions of 2 elements. For the purposes of this course, we will call those elements 0 and 1. Those are the very same zeros and ones that we are all familiar with, we've been talking about all along. So for instance, we have our block sphere, which is a nice way of representing, say in this case on the left, that we have more of a contribution of 1 than 0. The one in the middle, we have more contribution of 0 than 1 because the arrow is closer to 0 than to 1. And then this case on the right is when we have an equal contribution. As a warm-up, does anyone happen to remember this block sphere on the right here, this equal contribution? What do we call that state? What do we call this state on the right? What do we think? It's one we've seen before. The other two we haven't really seen before, given a name to. Yeah, it's a superposition. Specifically, it's the plus state, right? So when we have an equal contribution, it is a superposition. In fact, technically, all of these states are superpositions. This one on the right is the equal superposition state known as the plus state. Awesome. Now, we have several ways of looking at this, but I don't know about you, but here it's a little hard to tell exactly how much of a contribution of 0 versus 1 we have, right? Here it's half and half, so it's a little easier. But here and here, the left and the middle ones, it's hard to know how much of a contribution we have. We can see that there's more of 0 than 1 in the middle, but to know exactly how much is tough. Vectors are one tool to help us understand that and represent that. So we can mathematically represent the contributions of 0 and 1s using vectors. So the vector on the left here represents the 0 state, and the vector on the right here represents the 1 state. One way I remember that is that it's a bit like looking at the block sphere head on, where the 1 up top means, hey, the arrow is pointing up to the 0 state. And the vector here on the right is like you have the arrow pointed down, right? Down in the bottom part of this to the 1 state. So this is our 0 state. This is our 1 state. Or another way of putting that is whatever values you have in here, the one on top represents the contribution of 0, and the one on bottom represents the contribution of 1, right? Similarly to how on the block sphere, we have the 0 on top and the 1 on bottom. So with this knowledge, we can say that the representation of the 0 state, again, is 1, 0. Where again, don't get tricked up by the fact that we have a 1 and a 0 here. The 1 here represents that we have 100% 0, 100% on the top of the block sphere and 0% on the bottom of the sphere. Similarly here, we can say we have 0% of the 0 state, the top of the sphere, and 100% of the bottom of the sphere of the 1 state. So these are the representations of the 0 and the 1 states, both in block spheres and vectors, and in fact in kets, because that's what we have here. So in fact, these are all 3 of the ways now that we have seen to represent qubits. So before I continue, these are important. How do we feel about this so far? Do we have any questions? Are we feeling okay? Are we feeling lost? How are we feeling about this?
Well, one of the weird things, I mean, I'm used to vectors being orthogonal X and Y here, and the fact that they're up and down is a little weird. So when we're computing magnitudes, I don't know. It's not comfortable. I understand what it's doing, but it's just weird.
Yes, no, this is a very good point. For those that are familiar with vectors, this may seem a little strange because we would really, without kind of confusing more people by going into it, really these would represent different things in a different context. What I would say is the block sphere is a very special tool to represent qubit states, and that alone, that's really it. So generally, whatever intuition or physical picture you have of vectors otherwise, you can still go with. So if you're familiar with this language, these are still orthogonal vectors. Technically, you could still understand it in the way that you'd think about them typically. The reality is that just qubits are a little more complicated, particularly because of this idea of phase. And a complex phase. Again, this is getting into concepts we don't need to know now, but just for those that are looking at this and wondering why this orientation when that's not what you're used to. The reason is qubits are just a little special in that sense. But nonetheless, the ideas of these being orthogonal in the same sense that other vectors like this would be still holds. And if you're not sure what any of what I just said meant, that's okay. We'll go into a lot of these concepts as we go. Okay, so let's look at converting kets to vectors. So first of all, we have the 0 state. So to warm up, I'll give everyone a moment. Go ahead on your piece of paper that you've got out in front of you, your notebook, whatever you're writing on. Go ahead and for each of these, write out the vector that corresponds to this ket. So to the 0 and to the 1 kets. Go ahead and do that now and give me a thumbs up when you're all done with that. So I'm seeing the thumbs up rolls in. And yeah, Amar, yeah, in some sense, we can say that vectors are just one choice to represent qubits, just like we can use kets or block spheres, and they have certain advantages and disadvantages. So yeah, they generally are. That being said, there are some deeper reasons why vectors make a nice choice for this, let's say. But that's something we don't have to go into here. We'll kind of see the consequences of as we go. Okay, so seeing lots of thumbs up, seeing a few answers, so let's go through. So first of all, the 0 state, again, 1 on the top, 0 on the bottom. So we have a 100% contribution here and a 0% contribution on the bottom. And then the other way around for the 1 state. Awesome. Now let's get a little more complicated. So what I'd like you to do is try looking at these states, and don't worry about normalization yet. You don't have to do anything to these. What I would just like you to do is, given these kets and the addition of them, I would like you to write the vector that corresponds to them. So take a moment to do that and give me a thumbs up when you're all set. Awesome. These are a little harder. Okay. And the thumbs up roll in. So let's discuss. The first one would look like this: 1 and 1. Again, we're not worrying about normalization yet. So if you're not sure why I'm bringing that up or what that means here, don't worry about it. And if you do, then, and you feel uncomfortable with this, which as you go on, you will learn to be uncomfortable with, that's okay. Any questions about this so far? Okay.
Actually, I can't understand it.
Yes, please. Okay, wonderful. So 0 plus 1. So we can add together vectors like this, which is to say that if we look here, 0 is 1 in the top and 0 in the bottom spot. 1 is the other way around. So if we want to add these together, and let me see, maybe I can make this a little clearer by annotating here. If we want to add these together, then we can say that basically, if we want to add them, then that's the same as saying 1, 0 plus, and I know the drawing is a little funky here, but stay with me. So saying 0 plus 1, which is what we were asking on the first slide, is the same as saying this vector plus this vector. Okay. What we're saying is how that works is you just add the numbers in the first spot. So in this case, we have a 1 contribution to the 0 state, in this case, a 0. So in total, we get a 1 plus 0 contribution. And then same on the bottom, a 0 plus 1 contribution. And again, pardon the, the drawing here. But basically, we're saying to add these vectors is to add 1 plus 0 on the top, and then the 0 plus the 1 on the bottom. And then we can just simplify that using some more basic math now, which is just 1 plus 0 is 1, 0 plus 1 is 1. And so we get out 1, 1.
Okay,
So
thank you.
There's quite a few steps, but yes, does that make a little more sense now?
Yes, thank you.
Awesome. Yeah. I mean, part of this is you just have to be told, if you've never seen vectors before, that that's how this works, right? That may not be obvious. That may not be the only way we'd have to do it. But for us, I'm saying, or we're telling you, this is how we choose to do this. And in fact, it will work out well for us to represent them this way. Okay. So we get 1, 1 based on that. So similarly, we'll get 1 over square root of 2 and 1 over square root of 2 here. Because what we're saying is we have 1 over square root 2 on the top plus 1 over square root 2 on the bottom. And again, there's a number of different ways to get to this answer, but what's most important is that you find one that works for you. So I'm curious now, particularly given the explanation on the previous page, does this make sense, or does the introduction of the coefficients here, the 1 over square root of 2, make things a little confusing again? How are we feeling?
So in the first part, instead of writing 1 and under 1, 0, are we writing this and 0 under this? I don't know how to say it.
Are you referring to this part on the right here, or this part on the left?
In the right.
On the right. Okay. So yeah, this we can just
right,
call it
yeah.
the number out front. So the number out front here, why don't I can write it in math as well. And again, I think that will just make it clearest. But again, it's okay if not. So we can call this 1 over square root of 2. And again, this is a little funny looking of a number. So also it's a little funny when I draw it, but it really could work the same for any number. We can say that these two are equivalent. So for instance, this is the same as writing this, where again, pardon my drawing, but basically we take this number and we just write it in front of our vector for 0, 1 over 0. Well, this is another thing that you kind of just have to trust me when I say this is how it works, this is how we choose to do it. This is equal to, and I'm just writing this part here, is the same as if we wrote this inside. So 1, and just for space, I'll do a little slash like this, square root of 2, 0. So that's how we can represent this first piece here. So that's just the first vector here. These are all the same. These are all different ways of writing the same exact thing. Okay, so basically we can distribute that in. That's kind of the math speak, the technical speak. We can distribute this coefficient in, so multiply it in. So any number times 1 is just itself, so 1 over square root of 2. And then any number times 0 is just 0. So we get 0 on the bottom. Then if we do the same thing up above, we'll get the same result, but a 1 over square root on the 1 over square root of 2 on the bottom. And so when you add them together, you'll get this. So again, it's a lot of steps. And this is where you really want to write down every single piece. And then you will be good. And I'll work on getting a better way of drawing in the future so that we can have a kind of a smoother view here. I'll also potentially see if I can just do a smaller piece here. Okay. how are we feeling about this? I know, again, this is not the only time you'll see this. This is not your one chance to understand this. It's okay if you're not totally clear on it, but I just want to see how we're feeling in general. Okay. So let's keep seeing examples. It's important not to get too focused on any one example, and particularly once you see several, you should end up starting to see the patterns more. So it's okay if that last example didn't make total sense to you, if it was confusing. See if you can figure out what these might be, and just take a guess, right? You're all starting to figure out what's happening here and all at different places in terms of understanding how this works. So take a guess as to how these work. If you get to a point where you say, I just don't know, just take a guess. What do you think most likely might happen here? What might this look like in vector form, right? And just start with the one on the left first. And if you have time, get to the one on the right. Okay, why don't we start discussing? So I'm curious to hear from you all before I reveal the answer. What do you think for this first one? What do you think? And what I'll say is it could be a little funny writing these out. What I would recommend is using commas between the elements, the top and the bottom. So saying something like this, for instance. Yeah, like Amar just wrote. So basically, I mean, however you want to do is fine, but typically that would be how we'd write it. So go ahead and share. Do you agree with that? Do you have a different answer? What do we think? So 0.5 and negative 0.5 are what we have so far. Awesome. Ooh, yeah, another way to write it. Yeah. So in fact, it would look like this. Now, if you want to write 0.5 instead of 1/2, that is totally fine. Because 1/2 is a little bit of a meaningful number, we like it. Because we tend to deal with funny numbers here, we will end up we tend to prefer fractions, and by funny numbers, I mean like square roots and things like this, and irrational numbers. So we like to deal with fractions as much as possible, but there's nothing incorrect about using 0.5 and negative 0.5. Yes. So we haven't gotten to normalization yet. We will get there in a moment. Currently, we're just working on just how we go from, say, kets to vectors, and then we'll look at normalizing them. So this on the screen is the correct answer, 1/2. Note this is not 1 over square root of 2. This is 1/2. Now, when we normalize, we may see some square root of 2s around, but currently this is just 1/2 and negative 1/2. Okay. And I will say, because this is technically not normalized, to answer some earlier questions, this actually does not represent anything physical. This physically is not possible. That's part of what normalization is. So we'll get into that in a bit. Okay. And then on the right, we get 2 and 3. So another way to look at this is any number in front of the 0 ket goes on top, and any number in front of the 1 ket goes on bottom. Right? So this is really like saying, okay, I have 2 times whatever goes on the top, or I have 2 on the top and 3 on the bottom, right? 0 on the top, 1 on the bottom. So the 2 goes up above, 3 goes down below. Awesome. Okay. Let's look at another one. So now we have some mixture of different things. What do we think here? For sake of time, I'm going to keep moving. I'm going to say it's in fact this. Again, whatever you have next to the 0 goes up top, and whatever you have next to the 1 goes down below. The 1/2 on top, 1/3 below. Just like in these examples, whatever was in front of the 0 or the 1 goes on top or on bottom. 1/2 on top, negative 1/2, no, negative 1/2 on the bottom, or 2 on top and 3 on bottom. Similarly here, 1/2 on top, 1/3 on bottom. Okay. So before we continue, I just want to see, are there any questions at the moment? I'm not expecting this to totally make sense at the moment, but just, are there any general questions that we have? Okay, awesome. So now we're going to practice identifying valid quantum states. So technically, some of what we saw before are valid quantum states and others are not. So let's review conceptually what this means, specifically this concept of normalization. So for vectors to be true state vectors, by which we mean vectors that actually represent a real quantum state, they must be normalized. So normalized is just the name of this particular property, and this is what we need our quantum states to be. To be a true quantum state, a vector needs to be normalized. When we have a vector, it represents a valid quantum state only when it represents the probabilities of measurement outcomes. In other words, the length of a vector must be 1, and by the length, we have this special formula that we'll get into. But basically, we have to somehow be able to relate the numbers in the vector to probabilities of outcomes, the probability of getting a 0 or the probability of getting a 1. In particular, we need a length of 1 because each of them corresponds to a probability. And so when we get those added together, we need an 100% probability. So that is what normalization is about, is making sure that you have an 100% probability of getting a state out. So if somehow, and don't worry about the details yet, the squaring and all of this, if somehow you have these numbers that represent the probability of getting 0 and the probability of getting 1, it doesn't really make sense to say that altogether the probability of getting 0 or 1 is 75%. Because there's no other states, there's no other possibility. What is that other 25%, for instance? We need an 100% probability of getting 0 or 1. Now, there may be different probabilities of getting 1 or the other, but there's no other possibilities. So we can represent probabilities with percentages, which is typically how we talk about them: 0% probability, 50%, 75, 63, whatever, 100. We can also represent them as a fraction from 0 to 1. So 0.5, for instance, would represent 50%. So to find the length of a vector, we have this formula. If you have a vector with a on top and b on bottom, then you do a squared plus b squared all square rooted. This is the length that needs to be 1. So square root of a squared plus b squared needs to equal 1. For those of you that may be a little more familiar with this, this is in fact the Pythagorean theorem. This is the length of a side of a triangle. If you're not familiar with that, that's okay. But generally what we're saying is if you have a vector with a and b as your elements, then a squared plus b squared, all square rooted, must be equal to 1. That means it's normalized. Okay. So let's practice, and I'll answer some questions in the chat while we do this. But let's examine some of the vectors that you found in the previous exercises. So we saw some other ones before. So let's take a look. You don't have to necessarily do anything here other than just say, is it normalized or not? Which is the same as saying, are they valid quantum states or not? So in particular, this one on the left and this one on the right. And yes, I can go back one slide. Yeah, there's a lot on here. Can I answer any questions about this at the moment? So in terms of why the length should be 1, the idea is that, let's say this, there's a lot of details on this page. Let me summarize it as the length of a vector, which is something we will get into. The length of a vector represents the total probability of getting some sort of measurement. Getting a 0 or a 1. That's what the length of a vector means. So it has to be 1 because that means that the probability of getting any measurement is 100%. So there's a lot of steps here. And again, we'll just get more practice with this. But let's say length of 1 is the same as saying an 100% probability. And I'm typing this in the chat so it can just go there for you to kind of look at and try to think about. But having a vector with length of 1 is the same as saying 100% probability of getting a measurement outcome, 0 or 1. We'll unpack how and why and what we do with these numbers and all of this later. There's a lot here that I'm kind of just asking you to accept at the moment, and we'll get more practice with calculating the length and all this. But at the moment, that's the idea, is with a vector with a length of 1 is the same as saying that you have a 100% probability of getting a measurement outcome 0, which could be 0 or 1. Okay. And yeah, there's some questions about the if you're familiar with the vectors, this idea of magnitude and direction. So this is the magnitude that we're looking at, right? The magnitude has to be 1. The direction is actually a bit related to phase. It can be related to where it's pointing on the block sphere, but if you're, as was pointed out, if you're familiar with what the direction looks like in typical settings, it is a little strange of a connection to the block sphere. And I would say I wouldn't worry about that too much. More, we can think of it as this idea of phase, which we will be exploring later. But generally, it is this sense of phase, this sense of combination between states. So basically, if you have a vector that's purely 1 on top and 0 on the bottom, or vice versa, you have a purely classical state. The moment you get any sort of actual direction out of it between those, that represents something quantum. So in some sense, the direction is related to this quantumness, if that makes sense. Okay. So the basic takeaway of this is if you square both of the elements in your vector and square root it and get 1, then it's normalized. So let's look at an example. For instance, 1, 0. Well, if and I'll annotate again. And any way to make this. Okay. If I make this Bigger. Okay. So in this case, we have 1 squared plus 0 squared. And then we want to square root the whole thing. That is the length. That I'm telling you is the formula for the length. So that's 1 squared plus 0 squared. That's the same as saying the square root of 1 plus 0, which is the same as the square root of 1. And that equals 1. So in fact, this is normalized. So I'm walking through all the steps here. Particularly in the beginning, if you're not as familiar with this, I'd really recommend you do this. Take it one step at a time. Don't try to rush ahead. Just fill out the square root of a squared plus b squared, the square root of the top number squared plus the bottom number squared, and then go from there. This equals 1, so we're good. But on the right, we have 1 squared plus 1 squared, and we square root the whole thing. Well, that's the square root of 1 plus 1. 1 and 0 are easy numbers to work with. That's part of why we choose them. That's the square root of 2. This is not 1, right? It just isn't. It's a different number. In fact, it's greater than 1. That's a problem. That means this one is not normalized. So this is how you check normalization. This is also the same as saying we're checking the length. This number that I'm calculating here in both cases is the length of each of these vectors. So, in fact, you can see that this one is normalized on the left and this one on the right is not. To think of that physically too, the one on the left is saying we have an 100% contribution to the 0 state and a 0% contribution to the 1 state. That makes sense. Okay, that's 100% chance that we'll measure the 1 state. That's what that means. But this one on the right is saying that you have an 100% chance of 0 or 100% contribution of 0 and an 100% contribution of 1. That doesn't really make sense. This is kind of like saying that if you have a coin with heads and tails, you have an 100% chance of measuring heads at the same time as having an 100% chance of measuring tails. And while quantum physics can get funny with the chances of measuring things, that is just not allowed, not even in quantum mechanics. You cannot have a 100% chance of 2 completely different outcomes. So, in fact, this just physically doesn't make sense. That's what normalization means, is it's a check that you have some sort of logic behind this. This is saying you have an 100% chance of measuring 0 and an 100% chance of measuring 1. That is not physically possible. So this vector is not a valid quantum state. Let's look at some more complicated examples. So let's look at these. I think I'm going to walk through these just since we're getting started with it. And I want to make sure we're feeling okay. So I need to check the length of it. So what I'll do is, there we go. I already gave you the answer there. Let's see. There we are. Okay. So you saw the answers, but let's walk through why. So 2 squared plus 3 squared, and again, pardon the drawings, equals the square root of 4 plus 9, and that will all get square rooted, equals the square root of 13. That is really not 1. And I know I'm walking through that quickly. Feel free to use a calculator. Feel free to go through this at your own speed. Again, I really encourage you all to be doing this by hand right now alongside with me. Even if you feel comfortable with this, you know this stuff, it's just good practice. So square root of this ends up being square root of 13. In other words, this is the length. So this is the length right here. This is the length of this vector. And again, I know the drawings are a little funky, but this is the length of this vector. 2, 3 has a length of square root of 13, which I don't know exactly what that number is, but it certainly is not 1. And so this is not a valid quantum state. This one on the left, let's see, we have 1 over square root of 2 all squared plus 1 over square root of 2 all squared, and we'll square root that. It's really taking up a lot of space, but that's fine. So 1 over square root of 2 squared looks complicated, but that's really just saying 1/2. So that's 1/2, and I'd encourage you to use a calculator or double check that using your algebra skills, all of this, if you're not totally comfortable with it. So this is really the same as square root of 1/2 plus 1/2, which is the same as the square root of 1, which very nicely is 1. So in fact, this state on the right is normalized. This belongs to a physical state. This is a physical state. Just because the length is 1, because that is saying that there's an 100% chance that you will get some sort of state 0 or 1, that the contributions from 0 and 1 come out to give you an 100% chance. The state on the right is somehow claiming that you have a square root of 13 more or less fraction of a chance of getting a state out, but that's way more than 1. Also, it's like saying you have a 2 contribution to this 2 times an 100% contribution to the 0 state and 3 times an 100% contribution to the 1 state. This just doesn't make sense. Okay. So continuing on, in order to make sure we get through things, I do want to make sure we have time for talking about how to actually normalize yourself. So this is the last bit here. So the first bit is to check, is it normalized? So you find the length, again, square root of a squared plus b squared, same as the Pythagorean theorem. If it's 1, it's normalized. If it's not, then it's not normalized. It is not a physical state. What we can do is we can actually normalize a state. We can say, okay, I can actually take a vector that is not normalized and make it normalized by just dividing by its current length. So we can take the same number that you calculate and divide by it. So like where we have the square root of 13 in that last example, you could just divide that vector by square root of 13. And in fact, you would get a normalized vector. And I encourage you to do that out. So as we saw, this vector could somehow represent an equal contribution of 0 and 1, right? There's an even contribution of 0 and 1. But as we talked about, it really doesn't mean that, because it actually means you have a 100% contribution of 0 and a 100% contribution of 1. That's not physically possible. So we need to somehow normalize it. So jumping ahead a little bit here, but this is how you would do it. Because in part, the length of 1, 1 is square root of 2. The square root of 1 squared plus 1 squared, it's the square root of 2. So we divide by that. Now we get out this state, the plus state, in fact. So this is actually a condensed way to write the plus state. How would we do this state? And is this normalized? So there's 2 things here. 1, how do we write it as a vector? And 2, is this state normalized? Is it a valid state? What do we think? Go ahead and answer in the chat. First of all, is it normalized? And then secondly, what is it in vector form? Or the other way around, whatever works for you. Yeah, okay. Let's get in the mixture here. Yeah, so in fact, this state is normalized. It is normalized as is. If you look at the contributions, the negative, by the way, just squares away in the length formula because you just square it and you're good. Keep in mind these parentheses as well. So this 1 over square root of 2 is multiplied by both of these pieces. That's very important here. Otherwise, it would not be normalized. But this is in fact a normalized state, and it actually corresponds to the minus state, the one that we've seen over here in the block sphere a million times. And up until now, this probably hasn't made a lot of sense. I know we got a sneak peek of this before, but now we can really see where that minus in the minus state comes in versus the plus in the plus state, right? So the plus state is like this. Technically, we could think of it as plus plus in front. And then here we have a minus sign that represents the minus state. That will actually become very important as we go. So we only have about a minute here left. There's plenty more practice we can have, and we will have. What I would say is one last piece I want to focus on will be the probabilities. But before I get to that, I just want to get a sense of how we're doing. 1 to 4, you do not need to be totally on this, totally 100% getting it. But I'm just curious, how are you feeling? Feel free to send a number. And if you have any comments on what you're feeling, I'd love to hear that as well. Any particular things dragging this number down, or anything you'd like to see more of, get more practice with. Getting some complex numbers in there. Complex numbers for complex topics. Okay. Awesome. So we won't go into it, but the last thing I will say is those squares that we've seen, those squares that go into the length, those actually represent the probability of measuring. So in this case, up top, we have 1 over square root of 2. Well, when we square that, like we do when we're finding the length, we get 1/2, and that actually is the probability of measuring 0. This is called Born's rule. This is something we lightly saw last semester as kind of a sneak peek, and something we will see much more this semester. So that's kind of the new skill that I want to throw out at you just in the last moments here to get you thinking about this. But right now, I'd really like you to just focus on what vectors mean and how they are normalized and what their lengths are. We can look more into this as we go. Okay, so that is where we will leave it today. I will stick around for any last questions, but otherwise you are free to go. Have a lovely day and enjoy the rest of your week. And I look forward to seeing you next week to keep going on with the linear algebra. Have a great week, everybody. Bye, everybody.
A question.
Yeah, please.
Why is the square of the contribution the probability? Why not just any other number? Why not the cube or?
Yeah. There's 2 answers I can provide for that. One of them is that's just what seems to match up to physical reality. And that's really kind of the physicist's answer is when we represent numbers in this way, we do the squares like this, that seems to work. That matches up with what we do. We can actually run experiments and show that this corresponds to, say, the probabilities every time. And this is how to calculate something like the length of a vector and check if it's physical or not. So that's kind of the physicist or scientist answer is the experiment says so, it works with it, so we go with it. The deeper reason is a bit more, I guess, geometric. With these vectors really do represent something like a kind of triangle, let's say, in space or a vector in some sort of space. If you're familiar with these concepts, particularly something known as a Hilbert space, which we won't be going into this semester. And in that space, there's a very natural way to compute the kind of size of these things and the contributions of these elements. So I know that's neither of those are probably overly gratifying answers, but basically there's kind of the two sides of it, the experimentalist side, which is, well, the experiments match it, so it must be, and the more theoretical view, which is that it has to do with this idea of Hilbert spaces, as well as the fact that we are not talking about complex numbers like imaginary numbers, the square root of -1 here, but technically those are allowed in quantum mechanics. And so we actually need something that is even kind of a modified version of the square later on. So it's not even really the square, to be honest. It's a more complicated form that just becomes the square when we're talking about real numbers like we're dealing with. So I'm not sure your exact math level, but I get a sense that maybe you've heard of some of these things before, but if not, that's fine too. But yeah, so basically it has to do with that. Really, there's a more general way to combine these numbers, and the square just happens to be what comes out when we don't have any imaginary components. So there's kind of a variety of like answers, if that makes sense.
Is it somehow the multiplication of complex conjugates?
Yes, exactly. So it's the number times its complex conjugate. That's the amplitude of a complex number, and that's actually what we do. But otherwise, the formulas hold. So the square root of a squared plus b squared would just become square root of a times a complex conjugate plus b times b complex conjugate. And that's generally what we would do. That just becomes a squared plus b squared in these cases.
Yeah, thank you.
Yeah, of course.
Sir, I had a question.
Yeah, please.
So A and B can never be 0 at the same time, right? Because if that happens, then 1/0 would be not defined.
Yeah, awesome. So that's very true. So basically the vector 0, 0 would not be physically possible. That is also not normalized. We can check that by looking at the length, but also, as you said, it just doesn't make sense if you look at it. That's like saying there's a 0%.
Because it would be under root 0, and if we normalize it, it would be 1/0, which is not defined according to math.
Exactly. Perfect.
That would be like saying there are no states. Like
Exactly.
Of saying that.
Yeah, it's fun to kind of think about what these kind of things would mean. Yeah, a 0, 0 state would kind of be saying there's no contributions from 0 and no contributions from 1. But then what is there? So in fact, yeah, that's kind of the physical picture of why, and it is a good thing that the math backs that up, right? This exactly what was pointed out about the normalization not working out.
Okay, thank you, sir.
Yeah, of course.
Thank you, sir.
Yep. All right, everybody. Have a wonderful week.